Okay. Chapter 19 is about thermodynamics. Okay, but we will look into two more thermodynamics um, values or functions. Let's take a look at the first one. Okay, before we get into that, let's talk about spontaneity, meaning that the ability for the reaction to happen on its own without us having to push the reaction to happen. For example, something like the combustion of methane. Okay, in the presence of oxygen, we know that we can burn methane, right, at the room temperature, and then the reaction will happen immediately and produces carbon dioxide and water. That is what we call spontaneous reaction. Another one is if you have sodium metal and you put the sodium metal into the water, liquid water, the reaction will actually be quite explosive. And the product from the reactions are sodium hydroxide and hydrogen gas. Now, this reaction is very spontaneous, it is very exothermic. Okay, so now from these two examples, people are likely to make the assumption that in order for the reaction to be spontaneous, it has to be exothermic. But that is not true because you know that you can actually melt ice at any temperature above 0 degrees Celsius. So now that reaction is endothermic, but it is spontaneous, but only if the reaction is above 0 degrees Celsius. Another reaction is the dissolving of ammonium nitrate into the water. And this reaction actually gets colder because the reaction is endothermic, but it does happen. So, based on this slide, okay, I want you to understand that the reaction being exothermic does not mean that um, it is it you basically you cannot heat cannot be a criteria in determining whether the reaction is going to be spontaneous or not. Now we got to look into other functions that will help us determine whether reaction is going to be spontaneous or not. One of them is something called the entropy. Okay, so now in order to understand entropy, you have to kind of understand the dispersion of energy. So a good example is something like if you have a textbook, okay, and you're holding on to the textbook. The textbook has energy, it has potential energy. Now, as you drop the book, the potential energy now is being converted to kinetic energy. Okay, and the kinetic energy can be also converted into the form of thermal energy. Basically, when the book drop, as the book drop, it has to go through the air, run through the air, and then that causes friction, and then it generates heat. Okay, so now um, let's take a look back again before you drop the book. This, which is we call the initial state. At the initial state, all of the energy is concentrated as the potential energy. Now, as you drop the book, okay, and then the book goes down to the floor, at the final state, the energy is dispersed into different forms of energy. It becomes kinetic energy, becomes thermal energy. Okay, so basically, in entropy is dispersion of energy. So now let me talk about the second law of thermodynamics. Okay. Um, the second law of thermodynamics said this: a spontaneous reaction or spontaneous process can only is the one that result in an increase in entropy of the universe. Now, the word universe sounds kind of weird, but in chemistry, what we meant is the system and the surrounding; those two make up the universe. Okay, so let's take a look over here. So this one, you see that you have gas concentrated in this side of the glass container. Then when you open this valve over here, the energy, then when the gas particle, start to migrate to the other side, and then it just stays like that. Okay, so going from this side to this side, the reaction happens spontaneously. It happens spontaneously. It happens on its own. Why? Because it increases the entropy, which is disorderness, this dispersion of energy. So that's what drive the spontaneous reaction. But on the other hand, you will never see something that happen in this direction. Things become more orderly, or the concentration of the energy in one place. So that doesn't happen. So it is non-spontaneous. Now, keep in mind that entropy is actually, it is a state function, meaning that we don't really care which route it takes to get from initial state to the final state. All we care about is the difference between the initial state and the final state, just like enthalpy. Okay. Um, the entropy actually has its own equation. The equation is this: entropy, changes in the entropy, is equal to the Q, which is the heat of the reversible reaction, divided by the temperature. This temperature has to be in Kelvin. Therefore, the unit of entropy is in Joule per Kelvin. Okay, so now let's do some calculation. So let's say if you have the particle system, and it has the energy of 950 joule. So I want to calculate for the change in entropy. So it is going to be 950 divided by 298. Okay. So 950 divided by 298, what we have is 3.18. The unit is Joule per Kelvin, just like that. Okay. Now we talk about the second law of thermodynamics. Now we want to talk about the last law of thermodynamics. This is called the third law of thermodynamics. It says this: a perfect crystal. Perfect crystal can be an element, it can be compound, at 0 Kelvin will always have zero entropy, meaning that S is equal to 0. And then for the entropy, okay, if you look over here, we have bromine. Bromine has brown color. And if you have liquid bromine, the entropy is 152. If it becomes gas, it's 245. So that means that any temperature that's above 0 Kelvin, any element or any compound will have the entropy that's higher than 0. Basically, the entropy of any compound cannot be negative value. Okay. Now, entropy of the compound, we're not talking about the difference now. Okay. Now, however, what you notice over here is that in gas phase, the disorderness or dispersion of energy is higher than when bromine is in liquid phase. So that means the entropy of the gas phase will always be bigger than the solid state. Okay. Same over here. You can see this is ice. Okay, solid water. You can see that it's more orderly. Okay. Now, as you move on from ice to liquid, liquid become more disorder, more dispersion of energy. So entropy of the liquid water will be greater than the entropy of the ice water. And then when you go to gas, gas has the highest entropy. Okay, because there's more disorderness. Okay, here it is. Okay, standard entropy value of substance is the entropy gained by converting 1 mole of that substance from its perfect crystal. Okay, I'm gonna stop right here, and I will continue in the second slide.